In 2019, Nissan released its first ever variable compression ratio engine in the Infiniti QX50 SUV and the Nissan Altima. And these cars could do what no other cars could. Today, we're looking at the variable compression engine, which combines the best of both worlds by delivering the performance of a gasoline engine with the full efficiency of a diesel engine. We'll also see how it differs from the Mazda Sky Active engine. A turbocharged VCR engine used an advanced multi-link system to automatically adjust the compression ratio on the fly and at running speed, whereas conventional engines are limited to a fixed compression ratio and deliver the same balance of power and efficiency no matter the situation. The VC Turbo constantly adapts and raises or lowers the pistons variably and continuously to reach the correct compression ratio. What's remarkable with this technology is the fact that by changing the length of the piston stroke, the engine can infinitely vary the compression ratio in a range from 8:1 to 14:1 compression ratio. The motor's ECM thinks you need more power. The actuator lever slides on the control shaft to change the position of the multi-link system that rotates around the connecting rod's main bearing, lowering the piston in the cylinder. This reduces the compression ratio, allowing the turbocharger to pressurize safely without the risk of skipping cycles or pre-detonation. But when driving in top gear at high speeds, the system will work in reverse, allowing for as much compression as possible to improve fuel economy. Additionally, the engine's electronic valve timing and direct fuel injection system allow it to instantly switch between a conventional cycle and an Atkinson cycle. The compression ratio in an internal combustion engine is the maximum volume of the combustion chamber when the piston is at the bottom of its stroke divided by the volume of the combustion chamber with the piston at full compression, that is, at the top of the stroke. If the mixture is compressed to 1/8 of its original volume, then the compression ratio is 8:1. The compression ratio is one of the basic characteristics of any engine. It's laid down at the design stage and doesn't change as it wears out and ages. Most gasoline engines have a compression ratio of 10:1. Today, only select Mazda Sky Active engines made after 2012 have higher compression ratios of up to 16:1. Diesel engines are also capable of higher compression ratios due to the ignition characteristics of the fuel, which requires a lot of pressure to ignite. Increasing the compression ratio in a gas engine increases the efficiency of the engine. That's the key benefit. You get more power for the same displacement and fuel consumption, but at the same time, a high compression ratio increases the risk of severe engine knocks. That's why high compression ratio engines tend to run on high quality or high octane gasoline in order to run smoothly and not pre-detonate. So here's a question. If a high compression ratio is necessary for a better performing engine, then why don't car makers simply design the engine with a high compression ratio from the very beginning? Well, gasoline engines have a limit on the maximum pressure during the compression stroke, after which the fuel-air mixture no longer burns but detonates. It happens like this. To achieve higher power output at the same speed, more fuel must be burned and therefore more air is required. To accomplish this, turbochargers or superchargers are used to increase the intake pressure, but only increasing inlet pressure can lead to detonation of the fuel-air mixture unless the compression ratio is decreased. So, to prevent this from happening, the volume above the piston, that is, in the combustion chamber, must be sufficient. But the flip side of it is under a light load, the engine can lack power and torque. The solution is the ability to change the inlet pressure and adjust the compression ratio as required. And that's how the variable compression engine addresses this problem. The end result is that you can save on fuel as well as increase engine power when needed. At low speeds, a variable compression engine increases the compression ratio, and at higher vehicle speeds, it does the opposite. It decreases. That's because higher loads require lower gear ratios to increase power, while lower loads require higher gear ratios to increase efficiency and reduce fuel consumption. By now you're probably thinking, what about turbocharging? If a variable compression engine at low speeds increases compression and thus power, wouldn't adding pressure from the turbo increase the risk of detonation? These issues are addressed by using a compression ratio of 14:1 at low throttle to get the most out of every drop of gasoline. However, when you step on the pedal to get full boost and peak power, a clever mechanism changes the stroke of the piston, reducing the compression ratio to as low as 8:1. This allows the engine to continue to run efficiently without draining the fuel and on avoiding overheating the engine. That's why supercharging won't increase, but on the contrary, it lowers the compression ratio, while simultaneously providing high power and torque. The VC Turbo is also able to achieve a very high compression ratio of 14:1, like Mazda's naturally aspirated Skyactiv engine. Mazda Skyactiv engines work this way in all modes, while the Nissan engine works only at low speeds with light loads. When they increase, the mechanism moves into intermediate positions, lowering the compression ratio, and at high speeds or under full throttle, it automatically shifts the top dead center down, and the compression ratio drops to a minimum, which is 8:1. So what does this mean in real life? Well, the powertrain provides strong and confident acceleration from the very beginning and when overtaking other vehicles or when merging into traffic. As a result, the 2-liter VC Turbo is a performance replacement for the previous generation Ultima's 3.5-liter V6 engine, offering similar performance but with better fuel economy and lower emissions. By the way, fuel efficiency is 15% better compared to Nissan's naturally aspirated 3.5-liter V6 VQ series. That's with 25 miles per gallon city and 34 miles per gallon highway for a rating of 29 miles per gallon combined. Yet it retains the same performance as the V6 with 248 horsepower at 5,600 RPM and 280 pound-feet of torque at 1,600 RPM. The engine also uses 2 combustion cycles with electronically controlled valve timing, allowing the engine to switch between Atkinson cycles and conventional combustion cycles. It even improves fuel efficiency and optimizes performance when changing compression ratios. Of course, the extra heavy-duty components add mass. In fact, it's about 22 pounds to the engine's moving parts. But the design moves the crankshaft off-center, smothering out piston movement, unlike many inline-4 engines that are 2 liters or more. The VC Turbo engine doesn't use balance shafts to help offset the weight of the new parts. Also, dynamic engine mounts prevent noises from vibrating and entering the cabin, with vibration noise as low as 10 decibels. Believe it or not, VC Turbo technology was developed over 20 years ago. We're talking over 100 prototypes. Although variable compression engines have been around for decades, they only performed in laboratories for the sake of research in the combustion processes themselves. The first spark of the idea for a VCR engine was proposed by British engineer Harry Ricardo. That was back in the 1920s. One of Ricardo's first major research projects was on the problems of uneven combustion, otherwise known as knocking or pinging. To study the problem, he created a unique variable compression test engine. Actually, this eventually led to the development of the fuel octane system we know today. This attracted significant investment into improving octane additives and cleaning systems. By the way, this very drastic reduction in fuel consumption is due to the use of higher octane fuel, which is what allowed British aviators John Alcock and Arthur Brown to achieve the world's first ever non-stop transatlantic flight in their Vickers Vimy bomber. Then came the 1960s in America. Continental Motors produced a variable tank engine called the Continental AVCR 1100. By the late 1990s, other companies including Daimler, Volvo, Audi, Porsche, Honda, Ford, Suzuki, Peugeot, Citroën, Lotus, and even Russian Institute NAMI also conducted their own research into the VCR engine. But at that time, there wasn't any agreement on which mechanism was the most effective. In the year 2000, engineers at Saab introduced the Saab Variable Compression, or SVC engine, to the world. At that time, SVC was the most advanced and highly capable VCR engine. It featured a monoblock head which was displaced relative to the crankshaft, and the centric shaft raised or lowered the supports of one of the sides of the monoblock, into which the cylinder block and the head were combined. The volume of the combustion chamber changed, but along the way the position of the upper part of the engine under the hood also changed. This required refinement of the intake and exhaust system. Saab also offered a change of the compression ratio from 8:1 to 14:1. At the highest degree, the engine worked like an aspirator, with a clutch turned off the compressor drive. But the motor turned out to be temperamental, noisy, and moody at the bottom. But more than that, it was expensive and complex. The company itself eventually filed for bankruptcy, and that's why it never released this engine for production. Peugeot also designed their version using a conventional rod crank mechanism. That was in the late 2000s with the MCE5 engine. The Peugeot design works by varying the length of the rods that connect the piston to the crank. When the rod is shorter, the compression ratio is lower. When it's longer, the ratio is higher. Fast forward to recent times. 2019 Infiniti QX50 and Nissan Altima aren't the only models to use the VC Turbo. The new 2022 Nissan Rogue also has the VC Turbo, except it's no longer a 2-liter but a 1.5-liter 3-cylinder engine that outputs 201 horsepower and has better fuel economy. It boasts a combined fuel economy rating of 33 miles per gallon. This is a performance improvement of about 10% over its predecessor. But now you tell me, what do you think of the Nissan VCR engine? Have you driven a recent Infiniti QX50 or a Nissan Altima with a VC turbo? If so, please share your experience by commenting below. If you enjoyed the video, please like and subscribe. Thanks for your support. So if you never want to miss another one of my new car repair videos, remember to ring that bell.